Building software meant constructing a static, monolithic architecture, but AI transforms that structure into a complex, non-linear network of shifting nodes and data trails. Security has a timing problem in software development. The architecture is finalized, the build is scoped, and security is added as a late-stage review, often only after the system is built. This schematic represents the traditional security model. It relies on a hard network perimeter, like firewalls and VPNs, assuming everything inside that boundary is trusted. A VPN, or virtual private network, is a service that creates a secure, encrypted connection between a device and a network over the internet. With AI, this perimeter dissolves. These systems introduce a distinct attack surface shaped by early decisions regarding data flow and agent permissions, involving connections to external LLMs. An LLM, or large language model, is a type of AI trained on massive datasets to recognize and generate human-like text. Retrofitting security controls onto an AI architecture after it has been built is expensive and incomplete. It frequently requires massive rework that could have been avoided during the initial design. Secure AI requires designing confidentiality and trust into the system from day one. This is achieved through two architectural frameworks: confidential computing and zero trust. AI security is a structural design problem. It is not a compliance checklist to be completed at the end of a project, but a constraint that determines whether an application is an asset or a liability. This topology shows a multi-agent system coordinating AI agents across databases and APIs. Vulnerabilities occur first during inference, where sensitive data is fully exposed. Second, broad default permissions create a massive blast radius. A compromised agent uses authorized access to move laterally, infecting unrelated systems. This places all of your most sensitive data at risk, including patient health records, financial data, and proprietary operational information. Traditional network firewalls cannot stop a compromised AI agent that is already operating with broad, valid permissions inside the perimeter. Standard security protocols encrypt data while it is stored or in transit. However, AI models require data to be in use to function. In a standard compute node, encrypted data arrives and must be decrypted into plain text to be run through the model. At this stage, the data is visible to the host operating system and the cloud infrastructure provider. Confidential computing is the architectural framework designed to protect data during this specific processing state. This relies on trusted execution environments, or TEEs, creating isolated hardware enclaves within a processor. These enclaves ensure that the host operating system or cloud provider cannot read the data. Even with physical access to the hardware, the processing remains completely isolated and encrypted. This protects sensitive user inputs and an organization's proprietary model weights, which are the core numerical values determining how an AI processes and generates output. This adds infrastructure complexity and requires performance accounting during the design phase. It is a specific layer of defense, not a universal solution. TEEs isolate the compute environment, but they cannot prevent an agent from deleting a database if it holds the authorized permissions to do so. To prevent compromised agents from moving laterally, we must address the orchestration layer. This is where zero-trust architecture applies. The premise is to assume the network is breached, credentials compromised, and lateral movement a certainty. Zero-trust enforces identity verification and least privilege access at every layer. Every connection is validated continuously. If an agent designed to read emails is compromised, it strictly lacks the credentials to access financial databases, severing the pathway and containing the blast radius. Granting an AI agent broad access because it is convenient to configure is a common error in current AI deployments. Zero trust replaces implicit trust with minimal, explicit boundaries. This contains the blast radius even if a prompt injection is successful. Zero trust and confidential computing solve different parts of the problem. They work together. Zero trust controls access, while confidential computing protects data inside the processing environment. Implementing only one leaves the system vulnerable to either exposed data or overscoped agents reaching protected hardware. They are interdependent. Preemptive design begins with the first step, data classification. Architects must determine what sensitive data will flow through the system to decide where confidential computing is required. Next is permission design. Least privilege must be established before implementation. broad permissions become load-bearing over time, making them difficult and friction-heavy to remove later. Finally, AI-specific threat modeling must occur during the design phase. This involves mapping out potential prompt injections and output manipulations before the system is built. These steps do not require isolated security teams. They require a shift in how engineers design AI systems, treating security as a baseline constraint. By integrating these frameworks during the initial architecture, teams can build AI applications that are secure by design, remaining resilient and maintainable at scale.